Hello everyone. Artificial Intelligence and Machine Learning Unit 5 Neural Networks. In this video, we are going to discuss activation functions. In addition to that, we are going to discuss two learning algorithms, gradient descent and stochastic gradient descent. Activation function. What's an activation function? The previous video we discussed about perceptron, and that we had two stages. One is the pre-activation and the activation. In pre-activation, what it does, it aggregates all the inputs. Once the inputs are aggregated, it will check whether it is greater than 0 or less than 0. If it is greater than or equal to 0, it will be activated, otherwise it will be, that is, the output will be 1, greater than or equal to 0, less than or equal to 0, it will be 0. So the output is above a certain value, at the threshold value, it is activated. So this is the perceptron, typical perceptron. If it is greater than 0, this is activated, this output is 1. If it is less than 0, it is output will be 0. So the problem with this perceptron is not differentiable, because we have a spike here, so it is not differentiable. If it is not, what? So what? If it is not differentiable, so what's the problem, you may ask? Not differentiable means we cannot do back propagation. So in the coming videos we will discuss about back propagation. What's the role of back propagation? Through back propagation alone we will compute the gradient of the loss functions, then we will compute the weights and the biases. We will update the weights through back propagation alone. From the whatever error we obtain in the previous iteration, based on the error, we'll try to fine tune the weights through back propagation. Okay, we cannot do back propagation if the activation function is not differentiable. So this is a problem with perceptron. So we will go for another activation function called a linear activation function. The output will be linearly, that is proportional to the input. You will form a straight line, a constant gradient you will have. So that means if you differentiate, what you will get, you will have a constant gradient. In that case, there is no relationship to x during back propagation. Then sigmoid function is a very popular activation function, sometimes called the logistic function. The output will be 1 by 1 plus e power the input. Okay, input. So here this is a non-linear function. It's a non-linear function. Here there is a smooth, instead of an odd decision, perceptron had a odd decision. What we had, there is an odd decision. Okay, if it is greater than or equal to 0, it will be 1. If it is less than 0, that is, for example, you take a minus 0.001, minus 0.01, if it is 0.1. Oddly, there is a minute difference between 0.1 and the minus 0.1, but still the output for one input, the output will be activated, and for the other input, the output is not activated. So that is a very hard decision. This is so to avoid that, we are going for a smooth variation around 0. Around 0, we are having a smooth variation, not a certain variation. We are having a smooth variation. Since we have a smooth variation, so this is differentiable. We can do what? Back propagation. Still, this is not linear function. This is not a linear function. Okay, this is sigmoid function, sometimes called logistic function. Then tan h function, the output will be e power x. X is the input, e power x minus e power minus x by e power x plus e power x. This is scaled. We can call this a scaled sigmoid function. Output of this is just, this looks similar to what? Sigmoid function is sometimes called a scaled sigmoid function. This is a very popular one. ReLU stands for rectified linear unit. Rectified linear unit. You can see here. What is this? Like ReLU is f of x is maximum of 0 comma x. This is x. So if it is positive, means it will follow the input. If it is negative, means what? The output will always be 0. That is called maximum of 0 comma x. Input is positive, means it will follow the input, just like linear. But overall, this is non-linear. This is a non-linear function alone. Okay, it will look like linear. On the positive side, it will look like linear, but overall is what? It's a non-linear function. So it gives output if x is positive and 0 otherwise. It's a non-linear function. A combination of ReLUs is also non-linear function. So the sparse activation as negative values of x give you what? 0 output, because For negative values of input, it will give you what? The output as 0. So activation will be for most of them. For negative values of input, it will be 0. Output will be 0. So it will give you only a sparse activation. Sparse activation means most of them will be 0. The output will be 0. So in that case, when you go for a sparse activations, you can computationally efficient algorithms you can achieve. So through ReLU, the computationally efficient algorithms you can achieve. That is the what I can say is computationally efficient, since we are going for sparse activation. Sparse activation, most of them will be 0, and computations, number of computation required will be less. Okay. So a typical machine learning, before we get into the learning algorithms, a typical machine learning setup we will discuss. First one is the data. For xi we have yi, a label data can say, and we are going to model the relationship between the input and the output. How do we model? We can go for a sigmoid. First one is a sigmoid 1 by 1 plus, or you can go for w transpose x, or you can go for a quadratic relationship, or just any function you can go. In all the above cases, w is a parameter which needs to be learned from the data. W is the parameter needs to be learned. So this parameter is called model parameter. This is not hyperparameter. This is a model parameter. We will see in the coming videos. We will see what's the difference between model parameter and hyperparameter. So this parameter w is a model parameter which needs to be learned. Okay. So learning algorithms. What is the learning? So for how do you learn? So we are going to learn w. So how do you learn? For that to learn, so you need to have a learning algorithm. An algorithm for learning parameters w of the model. For example, perceptron learning algorithms. Already we have seen perceptron learning algorithm. Then gradient descent and stochastic gradient. Stochastic gradient we will see now. And we will have a objective function or loss function or error function. This function is to guide the learning algorithm. So this is the complete setup of any machine learning algorithm. Okay, this is for any machine learning model. You will have a data model, then you have to set up a model, then parameters, what are the parameters we are going to learn, and we will have a learning algorithm, and you will have the loss function. Then the gradient descent. Gradient descent is a learning algorithm, network learning algorithm, neural network learning algorithm. Inputs for the training is xi, yi, n, ii, n pairs of xy. You have a pairs. This is the input for the training xi, yi. What the training objective is? The loss function. How do you find w and b such that the loss function is minimized? What is this yi? Yi is the true value, and what is f of xi? It is the value as the output you are getting through the model. This is the through the model, whatever value you achieve for y is f of x. So here what function is given? 1 by 1 plus e power minus of wx is a sigmoid function. W and b, what are the w and b are the model parameters. Sigma using a sigmoid function, and w and b are the model parameters which we are going to learn through the algorithms. So our aim is to minimize the loss function. Okay. So how do you minimize this? First we will do it manually, then we can go for a gradient descent algorithms. Okay. So two data are given. One is 2.5, 0.9, 1.5, 0.2. X is 0.5, y is 0.2. Here x is 2.5, y is 0.9. Okay. We are going to obtain a curve. Where aim is to obtain a curve that should pass through these 2 points. Okay. First we will do it manually. We decide randomly. We choose w equal to 0.5 and b equal to 0. Okay. Let us check. How do you do this? What function we are using? For sigmoid function we are using 1 by 1 plus e power minus wx plus p. We are using sigmoid function. Okay. Sigmoid function. Activation function is sigmoid function, and we don't have any algorithm. First we will do it manually. Then we will use the gradient descent algorithm. Okay. Now use the loss function is L of w comma b is off summation. Why are you using off here? To make the differentiation easier. Here I didn't use the loss function is 1 by 2. Here I didn't use 1 by 2 here. Why are you using 1 by 2 here? Because when you differentiate, this 2 and 2 will get cancelled. Okay. That's why we are using 1 by 2 here. Now this is the loss function. Yi, you know. Yi, what is yi? for this point is 0.9 and for this point is 0.2. How do you compute f of x1? Use, what is this? This sigmoid function. Use w, use the value of x, use the value of w and b. What value we have chosen for w and b? We have chosen 0.5 and b equal to 0. You compute f of 2.5 and f of 0.5. You substitute, you will get the loss function as 0.073. But we want the loss function to be 0 or very close to 0. Okay. So either we do it randomly, we'll try some other values of w and b. So initially we have chosen 0.5 and 0.0. What loss function we have got? Loss function error, loss value we have got 0.0730. Now you decrease w. You keep b as such. Then you check the loss function is 0.148. And no, the loss function we try to decrease, but it's actually increasing. What we have to do, instead of decreasing w, we have to increase w. So 0.5 to 0.94. Then b you decrease 0.02 minus 0.94, 0.0214. Now, so now the loss function is what? Is decreasing. So you keep w, keep increasing w and keep decreasing b. So loss function decreases. You keep doing this. The w keep 1.65, b minus 2.08. So now the loss function is very close to 0. So you can decide w equal to 1.65. So this w and b definitely it will pass through these 2 points. So initially this curve, red curve, then the green, then the purple, then the blue. Now is moving in this direction. So it is moving against the gradient. So what direction we are moving? We intend to move in should be 180 degree with respect to the gradient. In other words, the move in a direction opposite to the gradient. So this is the gradient del. W2 is the gradient, and we are updating w. We have to update in which direction we have to do? Against the gradients. That's why we are putting minus sign here. What is del? Dou of the loss function with respect to w. This is with respect to w, and this is with respect to b. So what again I am saying, w and b are the model parameters which are learning through this model. Okay. Now we have a more principled way. So this is an algorithm. We are having this algorithm is called this algorithm is a learning algorithm. Okay, gradient descent algorithm. This algorithm is I can give it in the form of a table. Algorithm, gradient descent algorithm. So how do you use? First you initialize t. Iteration is maximum iteration give us 1000, while t is less than maximum iteration, wt equal to wt minus n. What is this n? N governs at what rate this adaptation is done, or this change has to be done. This is just like a step size. What rate? So if eta is high means it will change at a very fast rate. If eta is low means what? It will change at a slow rate. Okay. While t is less than maximum iteration 2, so wt plus 2. So this is updation for w and this is updation for b. Okay. This is the gradient descent algorithm. Next is stochastic gradient. Now we can see what is the difference between the stochastic gradient and the gradient descent. Stochastic gradient is algorithm updates the parameter for every single data point. For every single data point is updated. In gradient descent, the updation is done for every epoch. What is epoch? Epoch is one passover of the complete data. One passover of the complete data alone it will update. This is stochastic gradient. It is gradient descent. Here see WB maximum epoch for I in the range max epoch WB for XY in Z DW. This is updation. This is the updation. W equal to updation. This updation is done for, you can see the for here, for an indentation you can see here. This updation is done for every epoch, for every change of I. Here, but in stochastic gradient, for every x and y, this updation W equal to W eta eta dw. This is done. So stochastic gradient for every data, for example, epoch, we are having 1000 data, means 1000 data, one epoch is 1000. We are having 1000 data points, 1000 data points. So what is one epoch? One epoch is 1000 data points. In gradient descent, for every 1000 data points, only one updation is done. But for stochastic gradient, if we are having 1000 data in one epoch, 1000 data means we will do 1000 updation. 1000 for every data point we will do updation. Okay, that's the difference between the gradient descent and the stochastic gradient. Algorithm updates the parameter for every single data point. Now we have a million data points. We will make a million updates in each epoch. What is epoch? Epoch is one passover of the data. If we are having 1000 data points, we will pause the data points, complete data points, 1000 data. When you complete, pause all the 1000 data points, that is called one epoch. One step is one update. Okay, what stochastic? Because we are, why is called stochastic? We are estimating the total gradient based on a single data point, almost like tossing a coin only once and estimating the edges. So what's the? It is an approximate. What's the disadvantage of stochastic gradient? It's only an approximate, rather stochastic gradient. No guarantee that each step will decrease the loss, because it may increase, decrease, it may decrease, increase, like that. It will, we cannot expect it decrease every time. Let us see the, okay, epoch is for algorithms. This vanilla batch gradient, this is a basic algorithm. For that you will get 1, and stochastic gradient is n. Stochastic gradient is n, and for mini batch, this other gradient called n by b, where b is called the batch size. What is one epoch? I can say one pass over of the entire data. So n is the number of data points. So in stochastic gradient, we will have what? N data points. Number, because we will have what? N data points. How many steps you will have in one epoch? You will have n. But with mini batch, you will have what? N by b. These are the references I have made.